nice.
Quick introduction. Andrew is in our department. Same with Kutlu, and did his bachelor's in both maths and electrical engineering.
Well, I did.
Computer systems.
I did 2 undergrad degrees. I did a double degree in the wrong way. I did maths and physics.
Yeah.
Then I came back and did engineering.
Yeah.
And then I was a sucker. I did a PhD.
And he did a PhD virtually jointly between engineering and applied maths.
Yes.
So take it away.
Well, my partner May says I should always bring some realia. So there's a bit of a story to this. Before I was at the uni, I worked for Telstra, as Stephen did. And part of my duty in Telstra was to disassemble old telephone equipment and install new telephone equipment. And consequently, I acquired quite a lot of old hardware. And a lot of the hardware was like this. This is a smoothing choke out of a GPO power supply for a switchboard. And I full of hubris, I thought, well, I'll do a couple of measurements of this and I'll have it summed up. I'll have all its secrets. But I've been measuring it on and off for quite a while and I still haven't got all its secrets yet. But I can show you some of the techniques that are making progress on that. The other thing is, in terms of my hubris, when I first encountered electrical machines, this was the textbook I used, and I found it very complicated, but now I teach the subject, so hopefully it's not too complicated. But you can just get textbook models and you see that the kind of framework you put over reality, which is not quite true. I think and so what I'm trying to do is find a better framework to put over the measurements. So the next thing is the first framework we do, the textbook framework, is phasors. And phasors are not often described in this way, but they're like an inner product in a Hilbert space. You've got a kernel, which is that e to the minus j omega t thing. The 2 is a normalization factor. And this is actually all due to a fellow called Steinmetz, really brilliant fellow. And you get the expected value. Now, when you look at what an expected value is, it's an integral over a period. And so basically, you're multiplying a kernel function by a time function and integrating over a period, and that's a product in a Hilbert space. And the next question is, what if the function you had wasn't periodic? Well, you have to do that, and you integrate over a long time, and you make the time become very large. And what you find is that pretty well, whatever your function is, it will have periodic and non-periodic components, and the non-periodic components add up to nothing. So you get a phasor transformation of a constant at 0. You get a phasor transformation of any sine wave other than the frequency of interest at 0. And but within that frequency, and you're using 50 hertz in the mains or whatever, you can use this phasor approach. But what's going on there is you're mapping a function of time onto a complex number, and the complex number has a predefined algebra because it's a field. So that's basically what you're doing. If you sum it up very quickly, you find this is phasor transformation and that's inverse phasor transformation. And there's certain basic rules that can be derived fairly simply. A linearity, that if you have a linear combination of signals, you get a linear combination of phasors. If you do a time derivative, you get a multiplier. And this is like an operator, that it's a complex number that behaves like an operator. And you can do that any number of derivatives. And curiously enough, because of the 0 constant, remember all the constants disappear and go to 0. You can integrate very easily, and you can integrate as many times as you want. And all you do is just do the inverse of the differentiation. But this is integration with 0 offset, which is very common in phasors and in the harmonic domain. And you can do time shifts. And this comes up later on when we look at what the choke does, because the choke does a couple of things to signals. It tends to saturate, which pushes them through some kind of Taylor series. So you're getting squares and cubes of functions. And it tends to introduce time delays, because if you go right down to the magnetic level, you've got all these little magnetic domains that are flipping, and it takes them a finite amount of time to flip, and so you get a time delay. And this kind of domain, phasor domain, can deal with time delays, and so can the harmonic domain. And there's a few obvious things in that domain. Cos maps onto 1 by definition. You want cos with an angle to map onto that. And once you get that definition, then the mapping of sine is minus square root of -1. And function of any other frequency maps to 0, and any constant maps onto 0. You just throw them away, but you can't recover them again once you've thrown them away. So if you get a circuit, and this was from my textbook, I confess there's a typo there, so ignore the F. But basically you get a voltage, you convert that thing into a phasor object, you convert that thing, the current, into a phasor object, and you get some relationship. Now, the next question is, why am I hung up about these? Well, these are the terminal measurable quantities, so I can't really dig inside this device, but I can measure current and voltage at the terminals. So I want the terminal properties, and these are my terminal properties. And if I'm using the phasor domain, all I get is basically 2 numbers. That's as good as I can get. It might be a very complicated circuit inside, but I can't dig into that. I can't dig into the more complicated circuit. So that's all it is. Now, if I want to get the R and the L, remember these are complex numbers. I divide that one by, I do least squares estimation of the phasors. I divide one by the other and I get a real number, and I get an imaginary bit, which is the inductance. And I thought, wacko, I've solved this choke, I was feeling very smug. But in the student project, I got them to measure these things, and we did all the least squares fitting with high degree of accuracy. And we found that the value of the R you get depends on the amplitude of the signal, and the value of the L you get depends on the magnitude of the signal. And it seems to me that these are meant to be fixed quantities, but they're drifting around depending on what we're measuring. So we're using a bit like a rubber ruler, it's stretching depending on what we're measuring. And so it's not a very good way to model these things. So there's something wrong with that phasor model, basically. And one of the things that's wrong is that a lot of the signals you get are not sine waves. And once again, getting back to my students and their projects, I would like to put pure sine waves through this device, but generating a pure sine wave is tricky. My friend Keith Kickert has tried to do that with Class D amplifiers and feedback, and it can be done, but very complicated arrangement. And even if you shove a purely sinusoidal current through the device, by the time it comes through the device, the voltage you get is some nonlinear thing with lots of harmonics. So the next question is, how do you deal with these harmonics? And this goes back to basically to Fourier. In fact, it goes back further, Fourier, Euler, and then Cauchy. And they found that by doing certain types of integration, you can estimate parameters. And it turns out how you do your cutoff matters. If you do a hard cutoff at a single frequency, you get this thing with all the overshoots. It has a beautiful slope, but you get all these overshoots, and that's called the Gibbs effect. If you want something that's more reasonably behaved and you're prepared to tolerate a slightly smaller slope, then you can put that through a Bessel filter. And this is something else that was recommended to me by Keith Kickert. And you might say, oh, that's pretty vague, that slope, but look, I'm only adding up 7 terms. If I crank up the number of harmonics and the number of terms in the filter, I could get very good square waves with suitable cutoffs. and I can represent pretty well any periodic function I want using a sum of sine waves, so that's okay. So I can produce my periodic but not sinusoidal functions, which brings me back to my last bit of realia. You might say, oh, well, the choke's one way and the harmonics in the power system are one reason you might want harmonic domain. But of course, all the power supplies we've got these days are all switch mode, and they've got periodic functions in them which are not sine waves. So basically, the kind of technique I'm talking about should be applicable to any system which has periodic behavior, but it's not strictly sinusoidal. And that's the domain I want to work in. And we do need to use Fourier techniques, so we need to use Fourier and Euler and Cauchy and so on. And if you don't like these spiky bits, the Gibbs effect, then you have to be a bit careful about how you truncate the series. But that's only a technical matter. It doesn't affect the theoretical applicability of the technique. So the next thing is, do you remember how I said if you go back that when you do an integral transform, it's a product in a Hilbert space, and one of the nice things about Hilbert space is you've got a projection. So when you're doing a Fourier series or a Fourier transform, you're effectively doing a projection, and you need some basis functions. And this is going back to Cauchy. You need to use complex exponentials, which cos omega t plus j sine omega t. You need to use those. And use the projection idea basically to get your component. It's really just it's a product in a Hilbert space. And then you can do synthesis once you've got your coefficients. Once you've done all your inner products or your Euler integrals, you can sum away. Now this is where the theoretical people and the practical people might diverge. You see, if I'm measuring this choke and I look at it with my oscilloscope and I do a fast Fourier transform of it, I never get more than about 15 harmonics. So for what I'm doing, I don't need any bigger than 15. If I'm really, really fussy, I could push it further. But then I run into other problems. I might not have enough memory to store it in my computer and do the calculations. And then if I push it really fast, if I drove this with microwaves, we'd find this thing doesn't look like a choke anymore. It would look like an antenna. It would be radiating. And so the model we're measuring is not realistic given the application for the device. So at some point we're going to cut off. And because we cut off, all the operators that we use are going to be finite, even though in principle they're infinite. Perhaps an analogy would be if I had an op-amp circuit, I might have an op-amp with infinite gain, but none of my op-amps actually have infinite gain, but I can still use the infinite gain formula as a guideline to tell me how to design my circuit. The infinite case gives you a guideline, but if you want accuracy, you do have to truncate it at some point. So in practice, you match the physics and the bandwidth. And also, there's a bandwidth due to your sampling rate and the number of bits in your samples and your sampling device. I've been using a picoscope. It'll do, what does it do? It does 12-bit samples, and it in a frame, it'll do about 800,000 samples. So you just push the button and it goes, boom, here's your 800,000 samples. So it's quite amazing what technology will do nowadays. So the next question is, what if I've only got samples? I can't do an Euler integral. I could interpolate and do some kind of integration that way, but it seems better to use the least squares method. So you're trying to get an approximation of this. You're trying to compare the samples with the sum of your series. And you form a least squares application, but remember these are complex. And so you've got this least squares estimation over complex numbers. And it turns out that there's a few approaches you can use, and I did originally use Lomscargel, the long periodogram technique. That's complicated from a coding point of view, but it saves on memory. And when you're looking at a lot of samples, though, 800,000 samples, Lomscargel's got a lot to be said for it. But the output, once you do your least squares, you get a bunch of coefficients. And this coefficients is a great big array of complex numbers. And depending on what language you're working in, if you're using Python with SciPy or NumPy, it's a great big array of complex numbers. You might have to do a bit of checking to guarantee that it's genuinely complex conjugate. But basically, you get a big array full of complex conjugate numbers. So this is another way that I've been using, and this is, I've found that if you've got a model like this, that the coefficients times the data matrix gives you the measurements. You want to work back to get the C, and you form these normal equations. And it turns out that this leads to a theory of the Moore-Penrose generalized inverse. Now, it turns out that you can derive Moore-Penrose inverse from using the techniques of Wirtinger. Wirtinger was an Austrian mathematician, and he realized if you treat the C's and the C stars as though they were independent, you can take partial derivatives with respect to them independently. Now, you might wonder, why would you want to do that crazy thing? But you see, you can't differentiate a real number, a real function in the complex domain. It doesn't have a single, it doesn't satisfy the requirements. But it turns out if you use Wirtinger's approach, you can use C and C star separately, and you can differentiate a constant thing, a real thing, like a mod squared, with respect to complex parameters that way. And so basically you get the Moore-Penrose pseudo. When you do all that algebra, you get the Moore-Penrose solution. I wish I'd invented it, but unfortunately Moore and Penrose got there first. It's very good. It's not brilliant though in some ways. Remember, I push my button, I get 800,000 samples. I want to go do 15 harmonics. I need 15 negative ones, 15 positive ones. I have a big array of 31 by 800,000. And on some computers, when I run this, the computer just crashes because there isn't got enough RAM. So, of course, being an engineer, I use brute force, and I just use a computer with lots of RAM in it. But probably a better solution overall might be to use Lomscargel. So I might go back to using that. And you can weight the least squares depending on whether some parameters are more important than others. And all that really requires is just putting a weighting function in front of the C, and then you do the algebra again. So there's another thing, you get the C, but then depending on how you want to represent things, you may want to alter the way that you shape the function Freyer or Lanczos. Lanczos wrote some very good work on this, but Bessel smoothing is just the easiest to implement. And if you've got non-uniform sampling, you're not in trouble with the least squares nor with the Lomscargel. That'll work with both of them. In fact, Lom was an astronomer, and his measurements of variable stars were irregular, and that's why he developed the technique. So basically, you take a whole lot of measurements, you form this matrix, which is a wee bit on the large side, but if you've got a computer with enough RAM, you just crunch away and you get your complex coefficients. And those complex coefficients sit in a vector, and those vectors are part of a Hilbert space. So I've mentioned the word Hilbert space. So there's another interesting thing. Who established that the harmonic domain was a Hilbert space? And it turns out it was Godfrey Hardy, English mathematician, established this back in the 40s. You think about the timing, Hilbert space was invented by von Neumann and Hilbert, and it was applied by Hardy to the what we now call the harmonic domain by Hardy. And the first use that I can find of the words harmonic domain come from an author called Acher in 1989. But the trick is that it's a finite, as far as we're concerned as engineers, it's a finite multi-dimensional space, but we can use the infinite case as an approximation, as a guideline. We're using linear time invariant operators. So that's the other thing. The operators in this domain look like matrices. They look like big matrices full of complex numbers. Most of the usual ones, like integration, differentiation, look like diagonal matrices, so they're relatively easy to invert. And when you're talking about inverses, they're relatively easy to do numerically in a computer. On the other hand, if you had a large number of harmonics, you end up with a very large matrix, and your numerical methods may not be very accurate. So you may need some sort of iterative method to trim up your inverses when you do the inverse, but I don't think that's a very big issue. When it's referring to big gun here, the von Neumann algebra, strictly speaking, applies to the infinite case. But anything that I program on my computer has a finite number of coefficients. And that's physically realistic when I'm measuring a device like that. Now, the other thing about the Hilbert space, in order for it to be a Hilbert space, it has to be what they call a linear space. And Kolmogorov calls them linear spaces, but most other people call them vector spaces. They have to be associative. You notice I'm using this funny lopsided notation here. This is due to Dirac. I'll talk more about this a bit later, but these are called kets. And you add the two kets, it doesn't matter what sequence you do, they're associative. And not all the algebras we looked at today are like that, but the kets in this vector space are also commutative. And there's an identity element, a zero. You can add zero to something, it makes no change. There's an inverse element, you can negate them. And in fact, you have scalar multiplication in these, well, so you get scalar multiplication. And there's an identity element for the scalar multiplication, and distributive rule applies. And so we use these all the time when we do real algebra, so none of these are too surprising. But the thing that makes it really Hilbert, you know, what von Neumann and Hilbert really added is you have a metric space which has a metric, and the metric's related to an inner product. And in this particular case, it's a conjugate inner product. So this is where the bra part comes in. When you have your column vector of complex numbers, if you do a transposition and a complex conjugation, you get the ket. So the ket represents transposition and complex conjugation, and then you do an inner product. And this is the way I like to think of inner products. It turns out, once again, you do all the sums, and it turns out that it's symmetric, it's commutative, it's linear in the first argument, but because you can flip it, it's actually linear in either argument. And it's always positive definite. So you always get a number that's these inner products. It's a sum of squares, and each square is greater than or equal to 0. So you get a positive definite thing. It turns out there's a few other handy cheats. Depending on how you write conjugate symmetry, you can put a bar or you can conjugate them. When you do this flip, sometimes they use a dagger, the X dagger swaps, but you can conjugate them, and they're also conjugate linear in the second argument, as I said. So these, and it turns out that the complex Fourier series satisfy all these requirements, which is basically what Hardy showed. So then we've got the Hilbert space. It's got a norm, which is based on an inner product. And if you get the square root of the inner product, you've got your distance, which you can represent by a D or a fancy mod without the square. And so the numbers, the coefficients that we're dealing with are complex. They're a bit like column vectors full of phasors. But the inner product that we get is basically a real number. By the way, when you do apply the Euler formula with brute force to a waveform like a square wave, you get a whole sequence of terms, and showing that this sequence adds up to something simple requires using Cauchy sequences. So it makes certain assumptions about convergence of sequences. But once again, in reality, in the engineering case, we're adding up finite numbers of terms anyway. But in practice, if you actually look at Fourier transforms of real measurements, fast Fourier transforms of real measurements, they drop off very quickly with frequency anyway. Just a few things about bras and kets. I don't necessarily like all these bits of notation, but this is what the sort of kosher rules seem to be. That's your ket. Your bra is like a complex conjugate. You transpose it, you conjugate it, and you get the bra. Now, the inner product, I prefer to think of it like that, but a lot of literature write it like that with the brackets around one argument. But I tend to think of it as a product of a bra and a ket. And certainly when I code it, it's a sum of a product. When it's written in Python, it's more like that. The metric is basically just the mod of the two distances. And this is, the mod squared is a very handy measure of error. Now, there's something to be said about operators. Operators are a bit like the rotation matrices and things that we looked at earlier, but in this kind of world, things like D, the differentiator, end up being diagonal matrices full of those J omega things, but you get J times 1 omega, J times 2 omega, J times 3 omega, and J times minus 1 omega, J times minus 2 omega, and so on. Now, that gives an interesting problem because theoretically in a true Hilbert algebra, you wouldn't have anything unbounded, but if you try to invert the differentiator and integrate, you have a problem with the constant term, because the constant term, there's no single constant that works, so the default is to assign 0, but when you try to invert 0, you get infinity, and so to avoid that, the integral operator is usually integration with 0 offset, and the 0 term is zeroed out. But that means when you multiply the differentiator by the integrator, you don't quite get the identity. You get a hole in the middle at 0. So integration with 0 offset's not quite the inverse of differentiation. You can apply these operators to kets and you get new kets, new items of the same type. Just to think about operators again, a lot of the simple operators are diagonal, but I think by the time I've modeled this properly, I'm going to need to use operators that are non-diagonal, that have off-diagonal elements. and operators that are quite possibly not commutative. There's nothing in the rules says that the operators have to commute. You get adjoint, which is basically, it doesn't matter how you do your brackets. And you can have operators, you can flip the operator and operate on a bra, or you can operate on the cat. And you can, if you do that, you notice you've got a bra, an operator, and a cat. That gives you a single number, which is basically a matrix element. Depends on what your item is, but you can extract single elements that way. Expectation values, basically, everybody does quantum mechanics, and there's people who know a lot more about quantum mechanics than me. You can get your expectation value by applying the operator to your observables. And it turns out also that there are eigenvalues, and they're sometimes useful. And sometimes decomposing unity is useful. I should mention that outer products, this is a kind of outer product. Outer products are useful when you want to try and estimate cross products of power. If I wanted to look at all the power in an element, and I want to use the Rayleigh energy theorem or Parsifal's theorem or something like that, I need to do an outer product and then sum across the diagonals. So outer products are quite handy. Then this is something that I spent a lot of time teaching myself about, but I hope you guys get it faster than me, is that quite often you've got a variable that you measure and you've got another variable that you measure, this one, and you want to ask how much of this one is there in that one? What's the multiplier? And what's the leftover bit? Now, it turns out, and I think this is just a wonderful result, that the least squares solution to that is if I get the epsilon is the y minus lambda x, and I did a mod squared of that, and I do all the derivatives, I do the Wertinger derivatives and everything, it turns out that the least squares projection I get, the lambda value is that. And what's interesting about that is it's not only the least squares solution, but it's also orthogonal. And you might say, well, why is that useful? Well, it turns out that getting the orthogonal projections is a pretty easy thing to do because you just do some inner products. So you can do least squares estimation by doing inner products and getting ratios of inner products. So it's a very cheap and nasty way to get to least squares solutions. So you convert your time function to a Hilbert space function, to a harmonic domain function, and then you do a few dot products, and lo and behold, you've got your estimates of whatever it is you want. And classic operator that we might want to use is time differentiation. And the reason for that is because when you're looking at, say, the current coming out of a capacitor, it's the time derivative of the charge, which is capacitance times voltage. And when you're looking at the voltage in a choke, in an ideal choke, the voltage is the time derivative of the current. So the derivative operator comes up a bit, and the inverse of that, the almost inverse of that, the integration with zero offset comes up quite a bit. So here's,
I've got a little comment.
Yes, go on.
From the last slide. The quantities x cat and epsilon cat you're using with reference to the measurables, but usually in quantum mechanics they are complex column vectors, so they can involve a lot of entries. So when you are using in your context,
in the finite space, that mod squared of the epsilon, if I write my error function as y minus lambda x, and then I do epsilon transposed conjugate times epsilon, I get the mod epsilon squared.
yeah,
It's definitely a real variable. And because it's a real variable that I'm trying to differentiate with respect to a possibly complex number, I have to do the Vertinger thing. But actually, come to think of it, that's real, isn't it? Because that's ratio of two inner products, which are both real. So it ends up being real.
Yeah, but in quantum theory, these gets usually involve, they are complex column vectors, so they involve a lot of other quantities. So they are not a single variable in the sense you use in electrical engineering. Yeah.
Well, we'll have to talk about this later. But there is a difference. In quantum mechanics, you haven't got a finite sum, you're doing an integral over a continuous function. And they're different kind of beasts. But I can say that from all the work that I've done, both algebraic and numerical,
Yeah.
the mod squared of the epsilon is definitely a real number. Mod squared of anything is a real number.
Yeah. For instance, is the one the x ket you're using, it can represent the quantum state of a few qubits, a single ket. So it can involve dozens of variables.
Yes.
So.
Well, I think that's a difference between my finite,
Yeah.
integers that I'm using for my functions and the much more complex world of the quantum world. Once again, correct me if I'm wrong here, but the reason I use Hilbert space for quantum mechanics is you've got these partial differential equations, like the Dirac equation, the Schrödinger equation. You're turning them into ordinary differential equations by applying an operator to them. So you turn your PDE into an ODE by performing a transform on them. And that's a perfectly reasonable approach. But here, I'm dealing with a much more, even though I'm using this convenient notation, I'm dealing with much simpler object. When I code it up in Python, that object there is an array of complex numbers, and that array there is complex numbers. That lambda is potentially complex, but when I minimize the mod squared of the epsilon and I do all the algebra, I end up with that. When I do the Vertinger thing, and I do it either way, on the lambda or the lambda star, I end up with the same number. So there's only one unique solution in the harmonic domain case, and it ends up being a real number. And what you end up with is that supposing, for example, this were a voltage that I measured at the terminals, and this thing might be the current, and the lambda bit ends up being the real part. The part that the voltage in that thing that's in phase with the current, which is what I choose to call the resistive part. That's what gives me the lambda. The leftover bit has the units of voltage. It would be the voltage that you attribute to everything else. You might want to break that everything else down into other parts. So, well, a bit of it's an error and a bit of it's due to the model that we have for the inductor and so on. But the point is that by projection or repeated projection, we can do least squares estimation in this domain. It may be very wicked to do it in quantum mechanics, and we must have a chat about this.
Yeah.
But in this domain where all we're doing is looking at Fourier series.
I believe the reason we use this formalism, the Dirac formalism, is because these ket vectors usually are complex vectors with an infinite number of variables.
Yes, well, in principle, this would be infinite. As I said, in principle, you can have infinite harmonics. But if you went way up into the microwave domain and I did a quick sum, 500 harmonics, eventually you get up into the microwave zone and you could measure what that device does. But you'd no longer be measuring it as a choke, it would be more like an antenna. It would look resistive, it would radiate. A bit above that, if you went up to hundreds of kilohertz, the capacitance between the windings would be more important than the inductor. So it'll start off like a choke, non-linear choke. It would become like a capacitor and then eventually like an antenna. You could model that, but we just don't do that for practical electrical engineering. And similarly, if you were using it to model switch mode devices in your power supply, you might be switching in hundreds of kilohertz, but there's no point in going up to gigahertz. It probably does radiate a bit, and you might want to calculate what its EMI is and so on. But basically, at some point, we truncate. So really, in practice, these are finite vectors full of complex numbers. And I'm treating the column vectors as the cats and the row vectors as the bras. And you do a transposition and a complex conjugation when you're writing the Python code. That's what you have to do. But we must have a chat because I'm quite interested in learning more about quantum mechanics and the true meaning of these states in that world, in that domain, would be very interesting. But applying it, this one's okay. So once again, if this is my measurable thing, I push my button on my picoscope, I get my 800,000 samples, I do my Moore Penrose thing, and it calculates the harmonic domain representation of that voltage. I measure that current by measuring the voltage across a resistor in series with this thing. And I know what the resistor is, so I can calculate the current. I put that through software, I get my harmonic domain representation of that. And I need to use a differentiation operator. And I need an identity operator. Now, the trick is that I don't want to just do an inverse like I did with the phasors. Basically, what you want is in phase and quadrature phase components. And so to get the R bit, you end up using an inner product. And to get the L bit, use a different inner product with a D in it. Now, when we do that, I should mention something else. Once you know what the R is, once you've estimated that thing, you can estimate what the EMF is. EMF is a fancy word for voltage that's related to Faraday's law. So if you have a changing flux, it produces an electromotive force, which appears as a voltage. You could say, what's a voltage? If you have your pep electron on a string and you say, how much energy does that electron have? The voltage is really energy per unit charge, and it'll have a certain amount of energy per unit charge due to the flux, due to the magnetic flux. But you can calculate what the E is. Once you've got the E, you can integrate it to the flux, and you can get hysteresis diagrams. This is the current in amps, and I think these are pretty small, aren't they? This thing's rated at about 1.5 amps, but I'm well under the rated value.
So if you are using this formalism, I wonder if you use the quantum measurement theory via Born's rule.
Now uncertainty principle. No, I'm just thinking. Whenever you do Fourier, you realise there's always an uncertainty principle. Your delta F. The delta F delta T is a property of the Fourier transform, and there's a similar delta F delta T thing in the Fourier series. And you remember the slope on my square waves, the amount of time it takes me to ramp up, that's my delta T, and the delta F is how far I went out before I cut it off. And I can't do one without the other. I can't truncate somewhere without getting a bit of a slope on my square waves, and I can't get too much slope without going out forever. So there is a sort of delta F delta T principle here. but it's more like a time bandwidth product.
No,
I can't make a thing happen faster than a certain amount without having a certain amount of bandwidth to describe it.
No, by Baud rule, I mean taking the mod square of projecting the quantum state vector, ket vector onto basis vector, and taking the mod square of that, which gives you the probability of the particular measurement outcome. So that is a very essential element in the whole algorithm.
Yes, yes.
I guess maybe I could say I feel like the Dirac's motivation for this is just not so much in quantum, it's whenever you have a space and a dual space.
Yes,
And
yes.
Braz indicates are delivered.
But I think the probability interpretation is interesting, and I'd like to know more about that. But I don't see that as quite related to, if you like, classical electrical measurements. Since I don't think we're going to get quantum uncertainty in that choke. There are quantum phenomena. I mean, all those domains. Why are there domains? Why do they take a while before they flip? Why do they flip discretely? And they're all quantum phenomena. This little quantum island says we are one, we are unified. Oh no, we're going to flip. So there's definitely quantum things going on, but it's just at the level I'm measuring, I won't see them. I think that would
because
be
my impression, without the quantum measurement theory involved or Born rule involved, this formalism will be reducible directly to the usual standard formula. It will not give you any advantage in my view.
Oh, well, actually, because there's two aspects that make normal phasor theory ineffective, and the first is the chokes have nonlinearity. And how would I represent the magnetization curve of the choke? Well, I could do a Taylor series of it, and it's going to have current to the naught, current to the 1, current squared. When I do a current squared, and it's cos of omega t or something, I'm going to get some constant terms and some double frequency terms. When I do a current cubed, I'm going to get some 3 times frequency terms and some 1 times frequency terms. When I add all those together, I put my function through a Taylor series. Like I put a current through a diode, for example. I get this whole Taylor series, which ends up being a whole string of Fourier components. Now, when I represent that in the operator, it's not going to be a D anymore, but when I represent it in my operator, it's not going to be a diagonal element. It's going to spray out across the operator, and I'll end up with a great big matrix full of non-zero coefficients. So that's the first reason, is that in the harmonic domain, you turn nonlinearity into harmonic diversity. I think that's the way I'd put it. The second is that these magnetic domains take time to flip, so there's time delay in any magnetic device, and that time delay can also be represented very well as a phase shift in the harmonic domain. Each frequency gets its own little phase shift, but you see, you can represent the generation of harmonics and the time delays in the operators. And so they're the two things that I want from it. And this is not, I haven't got a citation right here, but this has been looked at before, that it has a tendency to linearize the modeling. You take this thing that's really nonlinear and you somewhat linearize it by having a more diverse operator. But getting there, you say, how do I estimate the elements of the operator? Well, once again, I've got to use more Penrose and generalized inverse, and the operator's got a lot more points in it than the harmonic domain representations of the functions. I might have 30 elements in my harmonic domain, 31 or something, in my harmonic domain representation. I'll get 31 squared, I get 900 odd elements that I have to estimate. And in order to do that, I need a lot more measurements. And So they need to be racked up, and if I'm finding that even estimating functions is causing my computers to crash, I need to find a memory efficient way of storing that. So that's a yes.
Andrew, just a very quick question. I know nothing about electrical circuits. Just how confident are you that the R, W, and L there are constant over a wide range of frequencies?
Well, they're not, and that's what I want to do. But you see, the thing is with harmonics. Once again, with harmonics, I replaced that. Instead of representing the choke as an L times d by dt, I just say, look, it's an operator. It's a flux thingy, and my flux thingy operator will be a quite complicated thing, and it might vary. It might vary substantially.
As far as I can understand from what you had on the next thing, you were estimating R and W and L as constants.
Correct, and so you can see why that's a limitation and why we need to use a more complicated operator than the DLD operator.
Yes.
But you're absolutely correct. The next step is to find a more complicated operator which allows for variation in frequency and time domain and time shifts. But the LD is still only a model. And if you look at the next one, if the inductor were a pure inductor, then this would be a straight line. And this is under very low current. So I've got low current, and strictly speaking, flux should be a linear function of time, and it sort of looks linearish, but it's got quite a clear structure. And it's quite alarming, really, because as I say, it's designed to take 1.5 amps. I'm putting 100 milliamps through it or something. It's got an air gap. It's been linearized, but the air gap still hasn't linearized the darn thing. So what that RW and the L are doing, or especially the L's giving you the slope. If you draw a line down the middle of that, that's the slope. But you can see there's an error term there that's quite significant. And it would be, as you correctly point out, made out of high harmonics. So the next step really is to replace idealized operators based on models in textbooks with a generalized operator. And the only way to get at that generalized operator is to do a very large number of measurements and then do the Moore-Penrose inverse or some equivalent.
Andrew, you've got a couple of minutes. Do you have more slides?
Okay, no, they've been asking questions. I'll just flip through. What I will say in the short time left is you can, if you've got linearized models, and this is another one from the old textbook, you can use multiple projections. You can pull this term out, and then you can disassemble that term. Because this is two terms in parallel, these are orthogonal to each other, and so I can pull the terms out. So I pull out that by measuring it at DC, I get the EMF term, I then do a projection, and I can get the current that's going through the core, and I can use that to estimate the core resistance. I can take the other part of the current, and I can use that to estimate the inductor. But you can see the inductor measurement I'm getting there is like a straight line down the middle, but you can see it's got quite an obvious tilt to it. So you're getting a very rapid increase in flux for a while, and then it starts to flatten out. And so to get that full shape, we're going to need a much more complicated operator. That's essentially, and you notice the effect is when you linearize the thing, this L goes from 0.57, and whereas before it was 0.3, and so from 300 millihenries to 500 millihenries, you can say, what's the inductance of this thing? Well, it might be 300, it might be 500. Do you believe me? It's been measured quite carefully, but the truth is that the inductor model that we use is quite faulty and quite inadequate, even for things like that. Even for things like that with very low currents where you think they would be linear, the linear model is inadequate. So what's the future work? if I want to look at high harmonics, and your point is completely correct, I've got to shove more frequencies through it. I've got to chop pieces out of the waveform. And the cheapest, most reliable way to do that is to chop pieces out of the waveform, and you can just use triacs to do that. The other thing is, if I want to look at the nonlinear way this responds to amplitude, I need a range of amplitudes in signals, and I'm using variacs to do that. But then the thing is, I'm going to need a lot of measurements to measure those nonlinear operators, and I'm going to have to do a lot of least squares and all that. And I need some way of systematically storing the data so it doesn't all end up in a shambles. And it seems to me it's such a big project that I need to store it in a database, SQL database. So I'll store the raw time data in situ, but all harmonic domain data will end up in a database. And then I can line them up in rows and work out the operators. I still have to work out essentially 30 by 30 operators. So there's a bit of arithmetic involved, but the computer's doing that. Moore's law is making these things faster all the time. So I have to extend the Vertinger calculus and probably some version of the Moore-Penrose method to estimate my nonlinear operators, which won't just be diagonals. They'll be these 30 by 30 matrices full of numbers. But the other thing is, if you look in the literature, there's no really good simple model for hysteresis out there. And it's my hope that this approach will be effective enough that we can use a linear model to describe what's essentially nonlinear behavior. It linearizes it within a certain range. And that's the purpose of the project. And this is what I'm going to be doing over the holidays, along with Alex's bootstrap.
I think it's time for the next talk. Yeah, can we thank Andrew?